Okay, so this is going to have an important new thing where notice that that the thing that we're multiplying the y derivative by, notice that's not a constant anymore. That's why. So this is going to be, we're going to get some more interesting characteristics here. So the first thing, as always, I'm going to draw the x and y axis. So that's kind of the first step that I'm going to take in the analysis of the differential equation. Of course, I'm drawing this all wrong. Oh boy, this is just exhilarating. Okay, so I just learned this new tool that will let me draw straight lines, so I'm not going to have that problem anymore. Okay, so that's the x and y axis. Now I just want to sort of highlight the part where we have the Cauchy data. So the Cauchy data is going to be on the curve x is equal to 0, and y is varying. So that's going to be the y-axis. So it's going to be this curve right here. Okay, I'm going to start here. And so I'm not going to draw the characteristic curves yet. We'll do the whole procedure. But for this problem, the characteristic curves are going to start here, and they're not going to be lines. They're actually going to be curvy curves, not straight curves. So they're going to look something like this. Actually, they're not going to look at all like that, but they're not going to be lines. Okay, so let's start doing the characteristic equations. And again, the reason I like to do this part first is because it's going to help me figure out what the initial values need to be. Okay, so x dot of s is going to be equal to 1. X of 0 is going to be equal to 0 because if I'm on the y-axis, x is equal to 0. Y dot is going to be equal to y. So now this is where the new thing is. Y dot is equal to y. And y of 0 is just going to be some generic point on the y-axis here, why not? And then z dot of s, okay, so again, since things are a little bit different, I just want to show this. Z dot of s, so z of s is always going to be u of x of s, y of s. And so by the chain rule, z dot of s is going to be equal to x dot times the x derivative of u plus y dot times the y derivative of u. Well, what is x dot? X dot is 1. Y dot is equal to y. Okay, and now this is just the left-hand side of the PDE because, as always, this part right here involving the partial derivatives is always going to be z dot. So z dot is equal to 0. So z dot of s is equal to 0. And then z of 0 is just going to be u of x naught, y naught, which is, so there's a typo here. That should be y. This is f of y. F of y. Okay. Okay, so I've basically been writing all day, and my hands are cramping. So let me erase this. Okay, so now let me solve the characteristic equations, but notice things are going to be a little bit different. So x of s is equal to s. Y of s okay. Y of s is going to be y naught e to the s. And then z of s is just going to be, so this is y naught here. Z of s is just going to be f of y naught. Okay. So that should say f of y, not f of x there. Okay. All right, so now what are the curves? Well, s y naught e to the s. So y of s is equal to y naught e to the s. Okay, so what does that look like? Well, it's going to be y naught times e to the x value. So the characteristic curves are going to be exponential curves, and when s is equal to 0, it's going to start at this point here. So now we'll have curves that look like this. Okay, and if I pick a generic point here in the plane, let's say AB. If I pick a generic point in the plane here, well, again, if I trace my characteristic back to the starting point here, which I will call 0 y naught. If I trace it back to the beginning here and kind of move forward along the curve right there, I know that along this curve, the PDE reduces to an ODE, and U of AB is equal to f of y naught sorry, the computer is really not working with me right now. So U of AB is equal to z of s. So in other words, I start here and I go s units along the curve that way. But z of s is just equal to f of y naught. Okay, so now if I want to figure out u of AB, I need to figure out what this y naught is. And so I have AB, I need to figure out, I need to sort of reverse it, trace it back to this y naught here. So I need to figure out what y naught is in terms of A and B. And just like before, I'm going to solve this system of equations. So I'm going to have A is equal to S, and B is equal to y naught e to the s. Okay, well, so this just tells me directly A is equal to S. So this says B is equal to y naught e to the A. So then y naught is equal to B e to the minus A. So then U of AB, this is equal to F of B e to the minus A. And again, I don't want my solutions to be written in terms of A and B. I want it to be written in terms of X and Y. So U of XY is equal to F of Y e to the minus X. Again, let's just verify that this does satisfy the PDE. So if I do the X derivative of F, I'm going to get minus. So if I do the derivative of this inside with respect to Y, I'm going to get, sorry, with respect to X, I'm going to get minus Y e to the minus X F prime of Y e to the minus X. And now I'm going to do plus y times the derivative with respect to y. So that's going to be plus the derivative of the inside part with respect to y is just e to the minus x times f prime of y e to the minus x. And this is equal to 0. So that shows it satisfies the PDE. And now if I look if it satisfies the Cauchy data u of 0y, this is equal to f of y, e to the power of 0. E to the power of 0 is just 1, so this is f of y. Okay, so it satisfies the problem. Okay, so the new thing here was that the y dot equation was not constant. So the characteristic curves were not lines for this problem.